Hello everyone. In this video we are going to talk about torsional vibrations of the shafts. So shafts are very important mechanical elements in industrial systems, and they are used to basically carry rotational power and through the gears or discs or anything that is installed on them. And many times it might happen that one end with respect to the other end undergoes a small rotation. Like one end is locked, fixed, and the other one end wants to rotate. In that scenario, this shaft will have torsion, and if this force is released, or if this initial rotation on the other end, which is not fixed, is released, then the shaft will go back to its original position. If the amount of twist angle is not large, it acts like a torsional spring and goes back. But since it has momentum, since it has angular velocity, it keeps passing the original point, goes to the other side, and it shows some vibrations. And if there is damping in the system, which most materials do, that torsional damping would stop after a few seconds or fractions of a second, depending on what we call the stiffness, the rotational stiffness of the shaft that we're going to see. So in this example, the axis of the shaft is the x-axis. Rho is the mass per density. Okay, so if the whole length is L and the whole mass is M, then this rho equals M over what? L. Okay, Ix is the second moment of area with respect to the x-axis. Okay, so this is the moment of area. The unit of this guy is basically meter to the 4 or inch to the 4. This is not the mass moment of inertia. We also have that one. I'll show you. You can see it down here, okay, in this area, and we're going to talk about it. So here we have an infinitesimal element of the shaft. You can see it over there. And we have the two twist angles on the left and the right side, theta and theta plus partial of theta with respect to x dx, and dx or delta x is the length of the element. And then the torque on the left side is t, and the torque on the right side is t plus partial of t with respect to x dx. So if we write the equation of rotation for this element, we have the total torque along the x direction, which is t plus partial of t with respect to x dx on the right minus t on the left, the total torque, which if you simplify, it's going to be partial of t with respect to x dx. This is equal to what? Equal to mass moment of inertia of this element times its angular velocity. Remember, in dynamics we had sum t equals j times alpha, right? Remember, this is about the center of mass, okay? And this guy, the unit of that is radians per second squared, and the unit of this j was basically kilogram meter squared, okay? That was called mass moment of inertia. And this is different than this Ix, but they are related to each other for this part. Okay, so that is the formula we are using. For alpha, we write it as second derivative of theta with respect to time. That's the definition of it. And for j, the way we want to define it is here. J is basically, the definition of j is integral of r squared dm, while Ix is the integral of r squared dA. So what difference between these two, between dA and dm, since it's a shaft with uniform thickness, with uniform diameter and everything, dm can be written as what? The mass of this guy, or a small element in it, and that can be written as rho times dv, where v is volume, and volume in this case is what? The volume of an infinitesimal element here on this shaft. If we call it dv, that is equal to this thickness dx times dA, right? So that is dA, the whole mass, if you call it dm. You see that, or dV, if you would call it dV, dV is clearly dx times that dA, right? So if I write it as dx times dA, you clearly see that if I bring this rho dx out, the result of that is going to be r squared dA, which is the same as ix. So if I multiply ix by what? By dx, by rho, which you see here I'm doing, this result is that j. Okay, so here is my equation number 1. And the second equation we have to write is about the angle. So the total twist of this element, which is the twist of the right minus the twist angle of the left, theta plus d theta minus theta, right? And what is d theta here? D theta is this whole term here. This whole term is called d theta. Theta plus d theta minus theta, which is d theta, is equal to what? Now this part, we bring it from solid mechanics. In solid mechanics, if you remember, the relation between theta, t, x, g, and I is what? T, if you remember, if you had a solid shaft with length L, TL over G times I was what? Was, and this I, you could have written it as J, but that J is different than the J we are using here. That's the unit of that, whatever it was meter to the 4. That was the angle theta. Remember, this was what you had from solid mechanics. If the length L was everything was uniform along the shaft. Now in this case, we are only writing it about the small element. So instead of L, the length is dx, and instead of the total twist of theta, it's only d theta. So we have to write it like that. Okay, and if you remember from here, the torque over d theta was called the torsional spring of equivalent of the bar or the shafts are in here, which is gi over what? Over L, or dx in this case. In general, this could be replaced by L. So this was that torsional stiffness, right? Or the torsional spring constant for a shaft, correct? So going back here, we have this formula, and here we bring this dx down to this denominator, so it becomes, and multiply both sides by ix over g, ix times g, you get t equals ig ix times g times d theta over dx. So one relation is this, one relation is that, and now we need to combine them. If you look in the equation 2, you have t. In the top one, you have partial of t with respect to x dx. So what we do is we take a partial of this equation 2 with respect to dx on both sides to get this term, and we then multiply by a dx on both sides. If you do that, this here becomes ixg. This is already first derivative of theta. When you take another derivative, it becomes second derivative of theta with respect to x times dx, which is this one. And then we set it equal to the right-hand side of equation 1, which is this. Then we get rid of ix, we get rid of dx, and we divide basically both sides by a rho. So you get g over rho, second derivative of theta with respect to x, equals second derivative of theta with respect to time, and that is this equation 3, which is the wave equation that we had in a basically bar, right? Remember, or beams, when I talked about in one of my earlier videos, I talked about the vibrations of the beams. We came down to an equation similar to this, right? We came down to something similar to this, and this guy here was the square of the wave propagation speed through the medium. So this is still the wave equation, and if you remember, the solution to the wave equation We showed that in that video that it comes from, we use separation of variables, and we said it is a function of x times a function of t. So we said something like, for instance, h of x times some, for instance, q of t. And then we did separation of variables. They both turned out to be constant, and we found that constant has to be negative. So both of the solutions are harmonic, like this and like that. The x solution is a sine of this parameter plus b cosine of that parameter. The q is c sine omega t d cosine omega t. Okay? And if you see, the frequencies of the time functions and the x functions are different. The time functions are just omega. The x functions are omega times the square root rho over g, okay, which is the reciprocal of that over a square root. And here is my function. It has 4 constants. It has a, it has b, it has c and d to be found. 2 of them, which are x ones, the ones for x, a and b, they have to be found from boundary conditions of the shaft. These 2 c and d, which are time constants, they have to be found from initial conditions. Okay, so since this is second order both in time and position, we need 2 boundary conditions, 2 initial conditions. And so now let's go ahead and look at the specific scenario, specific boundary condition, and see how we can find some of these. So the simplest scenario that you can have is one end of the shaft is locked, is fixed, and the other end of the shaft starts to rotate, okay? So here, for simplicity, again, we go with the shaft that has a constant rho, a constant I all along the shaft. The length of it we consider L, the axis is X. One end we assume is locked, the other end is gonna twist. For instance, like what? Like if you have a motor and a gearbox, right? So this is the shaft going into the gearbox. Something like that. And this load that you're spinning here, this is your load. This load, you stop it momentarily. That means all of this going to be stopped, right? So this end has to stop, but the motor still trying to what? Trying to apply the torque and trying to spin this other end, right? This is where this shaft and this other shaft will be subjected to what? To torsional vibration. If first it's just a static deflection, but if then all of a sudden you release this and it can move again, right? So the system is not locked anymore. Then this guy is going to do what? Is going to do some vibrations. And if you let this T also go, basically. Or even if the T is there, you're going to see a combination of basically transient vibration and rigid motion. So here, this is what we have. This one end of the shaft that is free, fixed, that means theta added should be 0. So at x of 0 here, theta is 0, that means b has to be 0. Why b? Because if we go in and take a look, if we plug in x of 0 in this equation, what do we get? X of 0 makes this whole term 1, this term goes to 0, and it's 0 for any t. So this part cannot be 0. Their first term should be 0. And the only solution for first term, the left-hand side to be 0, is that constant b has to be 0. Okay, so b is 0. Therefore, your only x solution is this a sine of omega square root rho over gx. And now, at the other end here, we can put a torque, we can put an angle or anything. Here, for simplicity, we just say this end is free. So this end is free, so t at this end is 0. If t is 0 and this other end is fixed, where do you get the vibration from? The vibration comes from some initial condition. So basically, at this end, theta at point L and times 0 is not going to be 0. It's going to be equal to some theta naught. Okay, so you initially twist this end and then let go. Okay, you're not going to apply a torque on this end. You're just going to twist it a little bit and let it go. So it's free vibrations, basically. If that's what we are looking at here is free vibrations. You see, we have not put any torque on this shaft. If we had any torque on this shaft, then this simple equation will be a little bit different. Okay, because you have to bring in the total torque onto this shaft. So here is, we are looking at the free vibrations. Okay, and now at the x of L, t is 0, but remember t was what? T was, if we go back to this relation equation number 2, you see that t was ix times the first derivative of theta. If that's 0, that means the first derivative of theta with respect to x has to be 0 at L. Now, what does that mean? Well, remember, last time we just found that since b is 0, the only solution of x you have is this. Now here we take a derivative of this function with respect to x and then plug in x of L here, so that sine becomes cosine. This frequency comes out times cosine of that times L equals 0. Now this first part, which is a times omega something, that cannot be 0. A cannot be 0 because A is 0 and B is 0, then the whole theta is 0, which is trivial solution. Omega is the frequency, cannot be 0 because that means rigid motion. So the only part that has to be 0 is this cosine term here. This cosine term is the only term that can be 0, such that still have a solution. Now, if cosine of something is 0, that means that thing is n plus 1/2 times pi, where n is an integer number, right? So it's a like 1/2 pi, 3 over 2 times pi, 5 over 2, negative 3 over 2, negative 5 over 2 pi, right? And if that's the case, then we divide both sides by L and divide by square root rho over G, which becomes square root G over rho, and that gives me omega, which is the natural frequency, and that is this equation 5. And here, since frequencies cannot be negative, this n has to start from 0. So it goes 0, 1, 2, all the way. So the system will have infinitely many natural frequencies for torsional vibration, free vibration. The smallest one is pi over 2L square root G over rho. That is the first fundamental frequency. And what is the mode shape? Well, the mode shape, if you remember, is this remaining sine function. So this remaining sine function, this one here, is your mode shape, sine of omega square root rho over gx times omega n, of course, which is going to be the nth mode shape. So the mode shapes of vibrations for this function are sine functions, and these are what? The natural frequencies. Now, this was one scenario that we looked at, and you might say, what about C and D? Well, C and D just come from what? Come from initial conditions. So right now, my solution is what? If I want my solution, my theta is A times sine times these, and then I can call A times C a new constant, and A times D another constant. Let's call them E and F. So you're going to get E times sine of omega square root rho over gx. By the way, this x is outside the square root. This thing times what? Times, and I can bring this E inside the bracket. So it's going to be E times sine omega t plus F times cosine omega t. Right? This is my function. And now I can plug in, let's say, at t of 0, theta at any x, and t of 0 is, not at any x, at 0 first, or L, let's put L, because we are interested in the other end. This is equal to theta naught. So what does that give you? That gives you that sine of omega L square root rho over G, which is just a constant, and plug in T of 0 here, this term will go away, times F times 1. This thing equals theta naught. And from here you can find F. F is to be theta naught over this guy here. So it comes like that, and that you can take reciprocal of it. It's going to be like this. So that is your F, and then you need another condition. Let's say theta dot at L and 0 equals 0. So you release it from initial velocity of 0, and then from here you have the F figured out. The derivative of this function, this guy becomes negative omega sine omega t. This guy becomes e omega cosine omega t. When you plug in t of 0, this will go away. You're down to e omega cosine omega t. So you get e omega, and cosine omega t just becomes 1. And that still stays at sine of omega L square root rho over G, right? This whole thing should be equal to 0. And this sine omega L cannot be 0, omega cannot be 0, so the only solution is E has to be 0. And F is that. Therefore, your total solution theta becomes what? Becomes that constant times sine of rho this x, and then sine of omega, cosine of, sorry, cosine of, because the cosine is the only term remaining. Let's see, cosine of omega t. This is going to be your solution. Now, one more thing I want to show you is one other boundary condition that might be interesting is when one end of the shaft is fixed, the other end is basically attached to a disk, an object that has a mass moment of inertia of J naught. Like, for instance, consider this shaft to be your drilling rod and this head to be your drilling head. And that J naught or J of O is not really something you can neglect. It's a very heavy object. So in this scenario, what happens to the boundary condition? Well, still at x of 0, theta is 0. That means that constant b is 0. So your solution is still this a part. Then at L, t is not going to be 0 this time. T, which based on equation 2 was equal to ixg d theta over dx at L. That is equal to what? That is equal to the inertial torque due to the load J naught. And remember here, if we had a mass with acceleration a, the inertial force of it is m times a in the opposite direction of a. So if you have an inertia of J naught with angular acceleration alpha, the inertial torque for it is J naught times alpha in the opposite direction. So this is what we're going to use here, J naught times alpha, and in the opposite direction, this negative is for opposite direction, and alpha is second time derivative of theta. Okay, so now we have to compute these terms, this d theta over dx, if you remember, since my theta is this a function here, when you take derivative, this omega square root rho over g comes out, this sign becomes a cosine, and for x you plug in L, so you get this whole term here, right? Of course, pre-multiplied by ixg. And then your time function, here you want to take 2 time derivatives. For any function that is harmonic like this, the second time derivative you can show that always equals negative omega, if omega is the frequency of that function, times theta for any harmonic, whether it's sine, cosine, or both of them. So I use this formula here, so it's going to be negative. This one is going to be negative of omega squared times theta, of course the theta at L, then this negative and that negative would cancel each other, and theta at L is this function, the sine function, and this J naught omega squared is here. Now you try to do some simplifications. You divide both sides by this cosine, so this sine becomes a tangent. Then you simplify 1 omega from both sides. And here, so that is that tangent term that you have. Then you divide both sides by this J naught omega that is remaining. So it is going to be what? It is going to be Ix divided by J naught omega. And then this G and that is square root rho over G, you simplify, it becomes a square root G times rho. So you get that. Then, if you look at this term here inside the tangent, you have it outside as well. How? Well, maybe not see it right away, but if I multiply both sides of the numerator and denominator of the right hand side, this Ix, if I multiply both of them by L like this, and pull this rho out of the square root, so it comes here, and then the square root becomes this. Now, first of all, this numerator, Ix times rho times L, this is the J of the entire rod or the shaft, okay? And then, remember the term we want is L omega square root. And you can have it here. This is the omega of it, this is the L of it, this is the square root G over rho. So if we multiply both sides by reciprocal of these terms, or basically bring these terms to the left-hand side, both this one, and this one, bring all of them to the other side, you'll get what? You'll get basically square root of rho over G times L times omega. And then on the right hand side, the only thing that is remaining is simply going to be J of rod divided by JO, right? Which is this guy here. Now, this term that is outside and inside the tangent, if I call it beta, which is a function of omega n or omega, the equation becomes beta tangent of beta equals J rod over J naught, which is a constant. And this equation is a nonlinear equation in terms of beta. So you have to solve it numerically for beta. And once you have beta, then you can find what? Omega n, because omega n is going to be what? Simply, it's going to be beta over L, right? And then divided by square root G over rho, or times square root rho over G. So once you find beta numerically, you plug it into this formula, and this equation, by the way, it has infinitely many solutions. It's not just one solution that this guy has. It has infinitely many solutions. If we call the nth solution beta n, then the omega corresponding to that is going to be what? Omega n. So your natural frequencies come from this formula, instead of what last time that they were simpler, just some half multiple of pi, right? This time the natural frequencies are different, okay? Something like that. And this is good in applications, as I said, where you have a heavy head attached to the shaft, and you want to find the natural frequencies in those cases, like when you design a drilling pipe or something. So hopefully this video was useful to you. You learned torsional vibrations in shafts, with some examples, and I'll see you in the next video. Thank you.